Okay, so today we're delighted to have Andrew Siemion as our colloquium speaker. Andrew got his PhD from UC Berkeley in 2012, and since then he's been the director of the SETI Research Center at Berkeley. So he's had the luxury of spending most of his astronomical career in Northern California, where the weather is great. Andrew is going to be talking today about a very important recent extension to SETI, which I think is much needed in the community, a nice injection of new blood and new money, most importantly, into the effort. And so, Andrew, I'll just let you take it away.
Thanks, James. Is my microphone on? Yes? Well, I certainly think it's much needed, so it's great to hear that from someone else. It's really a pleasure to be out here. I mentioned earlier during the ITC lunch that this is my first time to the CFA, so it's really exciting to be here for me and to talk about really my favorite thing in the whole world, which is the search for extraterrestrial intelligence. Breakthrough Listen is a new program, but before I begin, I want to make sure and acknowledge the tremendous amount of work that's been kind of going into SETI over the last 50 or 60 years, and Paul Horowitz, who's in the audience here, who's one of your locals, has played a big part in that. Also Jill Tarter and Frank Drake and all of the big names. And everything that we're going to do in Breakthrough Listen in the coming decade is absolutely kind of premised on all of that very fundamental work that's been done by others. And indeed, it continues to benefit from the input from a number of people from lots of places besides Berkeley. And I myself actually have a joint affiliation with two institutes in the Netherlands. So the last couple of hundred years, in my opinion, have been an absolute triumph of science in terms of astrophysics. We can trace the birth of the universe back 14 billion years. We can map the cosmic microwave background, the leftover radiation from the birth of the universe. We can track the formation of the first stars and the first galaxies, and we're starting to learn quite a lot about planet formation. We'll talk a little bit more about that later. We know a tremendous amount about the universe, and certainly some mysteries about the universe remain, but in my opinion, no greater mystery than life. These are stromatolites, and we know from fossils like these that are fossilized groupings of cyanobacteria that life began on Earth very, very early in its history, something like maybe 500 million years or a billion years after the Earth formed. And the origins of life very much remain a mystery. There's lots of work that's going into trying to determine how life arose, but the way in which the kind of stochastic laws of physics that we all know and love somehow gave rise to self-replicating organisms like these is a mystery. And even more of a mystery is the evolution of life and the fact that somehow life evolved intelligence. It evolved an ability to ask questions about the universe and to ask questions about our existence. And I'll take a quote from Stephen Hawking, who's someone that I like to quote, something he said actually at the announcement about Breakthrough Listen, and that is that a universe in which intelligence arises only once and a universe in which intelligence is arising many, many times are very different places, perhaps even on the largest scales. The implication being that it's possible that very advanced life, if it attains a very, very high technological capability, could eventually start to influence the universe on cosmological scales. We recently learned, of course, that planets are basically everywhere. That's the punchline. Nearly every star in our galaxy probably has a planet going around it, and other galaxies are probably fairly similar. But does life ever arise on any of those planets is very much an open question. And I think the question about sort of life like this, some sort of jellyfish that are floating around in a methane atmosphere somewhere, is really just a kind of a precursor to the real question that I think most people ask when they think about life on other worlds, and that is there any life like this? Is there any incredibly advanced life that perhaps has a technological capacity similar to our own, and maybe even has evolved a technological capacity much, much greater than ours, and colonized maybe large fractions of a galaxy, or maybe multiple galaxies? And this is the question that we're trying to answer in the search for extraterrestrial intelligence. So I mentioned this already. Many people in the room are far more familiar with this than I am. But of course, Kepler has been an absolute triumph for exoplanets. And in addition to answering the question that most stars have planets, I think even more importantly, it's answered the question about how many of those planets are potentially habitable. This is an animation that I borrowed from my friend Eric Pedagura, who had it put together for a paper he had out a couple of years ago, in which he did some analysis on the Kepler data to count the number of habitable planets that were detected around a handful of Kepler stars, and came up with a truly incredible result. Something like 1 in 5 of the stars in our galaxy has a planet like the Earth, at least in terms of the size of the Earth, 1 to 2 times the radius of the Earth and its equilibrium temperature. And so we might sort of, play around with this a little bit, and maybe it's 5%, or maybe it's even 25%, a little bit higher. But certainly a large fraction of the stars that we look at when we look out in the sky, something like 1 in 5 or maybe 1 in 6, could host a planet that's habitable, that could have liquid water on its surface, which I think really represents one of the largest shifts in our understanding of our place in the universe in some time, and certainly drives home the question that we ask in SETI, which is, of course, is there any technologically capable life on any of these habitable planets? We have other reasons to be optimistic about the possibilities for life. There are many experiments like this one. This is the Millerurey Experiment, in which you take some seawater and put it in a little flask here. And you heat it up and you evaporate all of the organic molecules that come out of here. You run them through a little spark discharge gap like this. So you have some carbon dioxide and ammonia and hydrogen gas, methane and things. And you allow it to exist in this little spark gap here for a little while, something like that would simulate the early conditions like we had on this planet for maybe lightning. And then you allow some material to precipitate out of this. And what you find is that you get very complex chemical reactions going on up here, and you get the synthesis of much larger organic compounds, including even amino acids. And this kind of experiment doesn't tell us sort of how life began, but it does tell us that the kinds of chemical reactions that we think were necessary for life to begin on this planet proceed relatively readily from basic organic constituents. We have other reasons to be very excited about the possibilities for life. This is something called a black smoker, which I think will be a video here, which is a hydrothermal vent at the bottom of the ocean, where an entire ecosystem exists just based on chemosynthetic bacteria. There's very little sunlight, virtually zero sunlight that gets down this far in the ocean. So there's an entire ecosystem of life that exists most fundamentally just with the chemical reactions and the energy scavenged from those by basic bacteria. So even though we think a lot about habitable planets and about the possibility of liquid water on the surface of extrasolar planets, it's possible that life could exist even in ecosystems that we wouldn't immediately consider habitable. Maybe planets that are far away from their host star, but perhaps have some kind of other energy generation mechanisms that can lead to the emergence of life. But again, sort of asking this question, I think, always brings many of us back to a different question, or a related question, which is intelligence a common outcome? Now, certainly it would be very interesting, I think, revolutionary if we detected an independent genesis of life on another planet in our own solar system, a moon in our solar system, or perhaps in the atmosphere of an extrasolar planet. But I think, ultimately the question that many of us want to know the answer to is there other intelligent life out there? Is there life that we could talk to, that we could converse with, that we could learn from? And that is the question that we ask in SETI. So we don't have any way of directly detecting intelligent life. We wouldn't have any way of detecting an orca whale on another planet. But we can detect technology, and we use technology as a proxy for intelligence. And we have lots of technology on our own planet that's readily detectable at very large distances. This is everything from high-power TV and radio, like the Sutro Tower here in San Francisco. It's about 10 or 20 kilowatts or so. Very high-power radar systems, planetary radar systems like they have at Arecibo, or the Deep Space Network, or even maybe high-power lasers. This is not something that we do a lot on this planet yet, except maybe for adaptive optics, as is illustrated in this picture. But we're moving towards laser communication systems with satellites and other spacecraft. So we could potentially be doing this in a few decades. Put a little finer point on that just to illustrate a couple of very concrete examples about this kind of technology and how readily we could detect it. This is the Arecibo planetary radar. This is the brightest radio transmitter, non-classified radio transmitter that we have on this planet. I should be careful with the people that are in the audience here. It's not exactly 2 megawatts. It's really one megawatt, and the other megawatt is burned into a water reservoir. It's frequently used in a continuous wave mode, which many people don't realize. But when Arecibo is used to determine just the ephemeris of an asteroid, so not imaging an asteroid or imaging a planetary surface or a moon surface, it's used in a simple, just sinusoid CW mode, and really a fantastic equivalent isotropic radiated power, which is just like the luminosity or pseudo-luminosity for the astronomers in the room. And it's really detectable across the galaxy. People argue about this in the literature, whether it's truly detectable across the galaxy or not, and it depends on a lot of assumptions. But certainly it's detectable out to a large fraction of the distance to the other side of our galaxy. And this is, of course, something that we have here on this planet. A lot of people, when I show that slide, are quick to point out that, well, yeah, Andrew, that radio transmitter is really, really bright because it has a lot of gain. And so it has a very high equivalent isotropic radiated power or luminosity, but that's only because it illuminates just a little tiny patch of the sky. That's true. And of course, that means that it would be difficult, sort of probabilistically, for us to detect one of those on another planet. But we also have very bright radio transmitters, similar radio transmitters, that are used for search purposes to look for objects. And a good example of that is this space surveillance system, or the space fence. Not quite as high an EIRP, but a very large fan beam, 120 degrees by 1.5 arc minutes. So we could imagine some very, very advanced civilization on another world that perhaps is interested in mapping the debris in their own solar system that might use something similar. And these are the kinds of things that we could detect in our radio experiments. So we can play the same game with optical signals. You take the most powerful pulse laser that we have here on this planet, or one of the most powerful. This is one at the Lawrence Livermore National Lab that's used for fusion research. It's a 5 megajoule pulse laser. And you pair this with something like a large optical telescope, like one of the Keck telescopes, and you come to kind of a startling conclusion that this thing could actually outshine the sun to 1,000 light years by several orders of magnitude. You get something like 5 photons per nanosecond per meter squared from this sort of construction, and from our a star like the sun, something like 1 in 1,000 photons per nanosecond per meter squared. So for the brief fraction of a second that this thing pulses, it could actually outshine the sun. Now again, we don't do this kind of thing here on this planet, but we could. If we wanted to, maybe we'd have to put it in space. But simply as a thought experiment, it tells us that the kind of technology that we have here on this planet could readily be detectable at interstellar distances. So there's lots of different types of technology that produces electromagnetic radiation, across the electromagnetic spectrum, and we don't really know exactly what frequency or wavelength we should search. And a lot of people are fond of making guesses about this. We should look at pi, or pi times hydrogen, or we should look at the 21 centimeter line, or this kind of thing. But really, we don't know, and these are only guesses. So we want to explore as much of the electromagnetic spectrum as we can from the surface of the Earth, because even with the Breakthrough Prize Foundation, we can't yet put our experiments in space. So this is just a plot of atmospheric opacity versus wavelength, and these little gaps, of course, are are where the radiation reaches the surface of the Earth. And so at low frequencies, we use telescopes like these, like LOFAR, mid frequencies, Arecibo, the Green Bank telescope. And then at optical and infrared wavelengths, we use facilities there. Again, always looking for the same type of thing, electromagnetic radiation that we know can only come from technology, or at least that's what we think. So I hope that if you weren't convinced already, I've convinced you now that it's truly a unique moment in our history. We simultaneously have the certainty that life could exist elsewhere. All of the necessary constituents for life to arise on another planet is out there in the universe. And we also have the technology to search for other technologies in a very comprehensive way. This sort of excitement about this has been recognized not just by scientists, but of course by the public as well. So this might come maybe as a bit of a surprise. So here's the Arecibo Observatory in Puerto Rico, probably the radio telescope that's most associated with the search for extraterrestrial intelligence, the most sensitive single radio telescope in the world, really a phenomenal place to visit and a phenomenal place to do SETI. And our good friends at the National Science Foundation says that we should probably close it or operate it with a much smaller budget. Certainly something I don't agree with. I should be careful. Maybe someone from this review committee's in the audience, but I think this is awfully short-sighted. Here's another telescope, the Green Bank telescope. This thing is virtually brand new. It really only began science observations in about 2000. It's the largest fully steerable telescope in the world. It has heterodyne receivers, radio receivers that can operate up to 100 gigahertz. It has an active surface that can deform to improve its surface accuracy at very high frequencies. It's in a radio quiet zone, so a federally legislated area that's protected from radio frequency interference, and you can probably guess where this one's going. The NSF Review Committee recommends divestment from the Robert Seaberg Green Bank telescope. So again, one of our best telescopes for conducting searches for extraterrestrial intelligence, and it might not be available to us. But we were in luck. About 10 years ago, a group of wealthy folks in Silicon Valley got together and founded something called the Breakthrough Prize Awards. And the idea is basically to take the Nobel Prize and put it on steroids, basically, in terms of the financial award. This is a $3 million prize. It's the most lucrative prize in science. And also to inject it with a little bit of social media. So they fancy themselves as the only black tie event in Silicon Valley. So we have a reputation out there in San Francisco of not really getting dressed up very often. But all of these guys do get dressed up for this. And the entity that puts this on is actually the same entity that puts on the Academy Awards and the Grammy Awards. And so it's a huge black tie extravaganza, very well catered, and a bunch of folks like these are invited to present the awards. Pharrell was actually the musical guest at this last year's breakthrough prizes. So in July of 2015, there was an extension to the breakthrough prizes that was announced, something called the Breakthrough Initiatives. And this is Yuri Milner here. He's one of the founders of the Breakthrough Prizes and the founder of the Breakthrough Initiatives, who was joined by Stephen Hawking and Martin Rees and Frank Drake. This is Annie Druyan. This is Carl Sagan's widow, for those of you that don't recognize her. And this was an announcement of an extension to the Breakthrough Prizes that would actually begin to undertake specific initiatives in science focused around the search for extraterrestrial life. This press event in July at the Royal Society was accompanied by a full-page ad, an announcement, call to arms, if you will, manifesto about the search for life, and basically a call to the entire world that now is time to find out whether or not we are alone, to actually try to answer this question. And I think what was really exciting about this is that it was signed not only by people that you might sort of expect to sign it, like, Jill Tarter and Kip Thorne and others, but also some people that maybe you wouldn't expect would sign such a thing, like Sarah Brightman, who's a soprano. Let's see, where is Seth MacFarlane, who's kind of an interesting character to sort of bring into the mix here. But really, I think very much capturing what the breakthrough prizes are all about, which is to make science visible and appealing to the world. And what better way, at least as far as I'm concerned, to capture the public's imagination and drive them towards science than to ask the question that every child asks when they look up at the stars: is there anybody out there? There were two initiatives that were announced that day. The first was Breakthrough Message. And this is something maybe you haven't heard a lot about. This is a $1 million US competition to design a message that we would eventually send to extraterrestrial intelligence. The subject of messaging to extraterrestrial intelligence, or METI, is very controversial. Some people think that it's a very good idea. Some people, famously Professor Hawking, think that it's a very bad idea because it's something akin to shouting in a dark jungle. We shouldn't sort of announce ourselves if we don't know what's out there. So an important part of this is that there is, at this time, no commitment to actually send a message. It's simply a competition to design a message. How would you communicate the existence of humans to another life form? And of course, just by thinking about this question, thinking about how it is that you would best represent humanity, it causes us to look inward and wonder how we are representing ourselves, and maybe how we should represent ourselves. The second initiative that was announced is the one that, of course, I'm talking with you about today, which is Breakthrough Listen. Breakthrough Listen is in short the world's most comprehensive, sensitive, intensive search for extraterrestrial intelligence in history. It's a 10-year project funded at a level of $100 million. We've announced three key components of the search. We want to search a million nearby stars, conduct a complete survey of the Milky Way galactic plane, and also look at 100 galaxies. The idea of the galaxies is, of course, that if intelligent life is very, very rare, but perhaps can attain a very, very high level of technological sophistication, maybe we should look at areas where we can get lots and lots of nearby stars in our telescopes. And galaxies, of course, the way to do that. The very far end of the luminosity function of extraterrestrial technologies. A couple of just sort of kind of buzzwords, buzz phrases. A day of Breakthrough Listen is equal to 1 year of any previous search. We can search much, much faster and much, much deeper than any search that's ever come before it. And we'll talk a little bit about how we get that level of sensitivity and speed in the search. And also, very importantly, more scientific data publicly available than any project in history. We want to engage the entire world in this project, and not just the public, but the scientific community as well. So all of the data that we collect from all of the telescopes that are part of this experiment are being made public as quickly as we can, in fact. And soon we hope that the time scale between recording data and doing some analysis and making those data public will be of order hours. And not just the data, all of the code, all of the hardware, all of the equipment designs, everything about the project is completely public. Yuri Milner said when he announced the project that he would like to create the app store for SETI, and to bring Silicon Valley ideology to the search for extraterrestrial intelligence. And it sounds a little crazy, maybe. I think when I first heard it, I thought, well, this maybe is just a Silicon Valley venture capitalist kind of giving his usual spiel, but applied to SETI. But we actually think that there's something to this. We think there is a nascent community of people with expertise in signal processing. Maybe not astronomers, maybe they're sonar technicians, or maybe they work in seismic research or something else, that could bring their expertise to bear on this problem. What we're doing is very, very difficult. It's very, very hard. It's lots of data, lots of interfering sources, and we'd like as much help as we can possibly get. And of course, the website for all of this is breakthroughinitiatives.org. There are 3 facilities that have thus far been announced that are a part of the project. The first is the Automated Planet Finder. This is a relatively small 2.4 meter optical telescope that's at the Lick Observatory in California. It's used primarily for radial velocity work on extrasolar planets, but we've gotten 10% of the time, 36 nights a year, to use this for optical SETI. And what we do is we just look for artificially narrow spectral lines, basically spectral features that are too narrow to be astrophysical. And we can do that because of this fantastic high spectral resolution Levy spectrometer that's on that site. Also, the Green Bank telescope, we've already talked a little bit about this. This is, again, the largest fully steerable telescope in the world. It's in this extremely radio quiet region that's federally protected from interference. It has a very flexible signal processing system that can actually deliver up to 10 gigahertz of dual polarization bandwidth to our instrumentation. So that means we can search 10 gigahertz of bandwidth at a go, 10 billion channels, if we have enough DSP available to us, signal processing available to us at the site, and nearly continuous frequency coverage from 300 megahertz to 100 gigahertz. So there's very limited multibeam survey capabilities of this telescope, but it's really fantastic for doing deep targeted searches of nearby stars. We also purchased about 20% or so of the Parkes telescope, which is very famous for its discovery of fast radio bursts in recent years. And the way that it did that is with a very nice multi-beam receiver system that they have on the telescope. It's 13 beams that operates from about 1.2 to 1.5 gigahertz. And this is going to be a fantastic telescope for doing surveys. So a large fraction of the galactic plane survey component of the project will be conducted with Parkes. But they're also planning to get a wideband single pixel feed, and that's probably going to come in about 18 months. That'll be something like 700 megahertz to 4 gigahertz. So we'll be able to do some nice targeted work with Parkes as well. There's also a possibility of getting something called a phased array feed on the telescope, which would really open up the field of view at 21 centimeters. So in addition to the telescopes, a really huge part of SETI in general and a huge part of Breakthrough Listen is the technology. If you want to be able to search 10 billion spectral channels at once at timescales of a few seconds, you need a lot of computing capability, very, very high data rates in this experiment, something like 200 to 400 gigabits per second when we're totally ramped up at Green Bank, which is something like, 10 or 100 times the recording of a VLBI data recorder, if you're familiar with that. So lots and lots of data to disk. Everything needs to be GPU accelerated, the entire search pipeline. Of course, interference, radio frequency interference. Our own technology is the problem in radio SETI. If it weren't for the fact that all of our technology was producing emission like we're looking for, things would be much easier. And all of this needs to be built with commodity hardware because otherwise it's just far too expensive. So we've been working quite a lot with the Casper collaboration. This is a group of scientists that are designing new instruments for radio astronomy that I know many of you are familiar with. And this group and the work that they've done for the last 10 years or so is what's made this possible. Again, the technology that we use is not limited to the radio. The Levy spectrometer is really a fantastic instrument in its own right. Something like an R value of 100,000 and an arc second, a meter per second velocity precision. 2.6 million, funded mostly by Ken and Gloria Levy. A private donation, and very nice for us as compared with the radio. This instrument already exists, so we don't have to build any fancy gadget to record the data. So a timeline of the project. We announced the project in July. In August of 2015, we got very busy with instrumentation development and planning our observations. We commenced observations with Green Bank in January. And we expect to begin with Parkes in October of 2016, October 4th, in fact. Our lead engineer for the project, David McMahon, loaned me these slides that I know some of the instrumentalists here will appreciate, which is how you build an instrument like this in only 6 months. Step one, you start with an existing antenna. That's very helpful. You use existing digitizers and gateware. This is really a very cool instrumentation innovation that we took advantage of here with Breakthrough Listen. We didn't bring a complete digital backend to the telescope as a whole. Actually, what we did is we took an instrument that already exists. It's called the Vegas spectrometer at the Green Bank telescope. And all we did is buy them a new Ethernet switch. So they were already digitizing this 10 gigahertz of data. They were feeding it into these field programmable gate array boards, and it was going through an Ethernet switch to a bunch of computers. So we just bought them a larger Ethernet switch and plugged in a whole bunch of our computers. And that allowed us to take advantage of a huge amount of infrastructure that already existed at the site and allowed us to get going very, very quickly. So we installed a new cluster. This is what the system looked like as of November. We brought about a petabyte of storage to the observatory. That effectively doubled the amount of storage that the entire observatory had when we brought it in. There's quite a lot of performance tuning that had to go on. Some of the computer folks in the room probably know what a lot of these terms mean. We can talk more about that later if you want. We're very excited. We got 6 gigabits per second to disk on each of our compute nodes pretty quickly, and we're actually getting about 3 times this at high performance. And so we're hopeful that we can actually extend our hardware a little bit farther than we thought that it would go. A big challenge and something that remains a challenge is, of course, integrating with the telescope control system. Our goal for Breakthrough Listen is that eventually the back end that we have at Green Bank and at Parks and with the APF as well in terms of the software pipeline is available as a facility instrument to people that want to use it. So if one of you has an idea about some other kind of target that we should be looking at, a globular cluster or the Earth's ecliptic plane or whatever it happens to be, you could either propose to us, to Breakthrough Listen, or propose to the observatory to use this fancy instrument that we've deployed to conduct your own searches. We were very excited to get first light December 30th of 2015, so just a day or two before we were scheduled to launch. This is the first detection plot from the experiment. This is the detection of a bright pulsar at L-band at 21 centimeters. And then sort of shortly after we got this result, we pointed it at the most distant piece of human technology that's producing radio emission, the Voyager spacecraft. And this is a detection of the carrier of Voyager. This is at about 8.4 gigahertz. And the sidebands of the communication system, this is where Voyager is relaying data still back to the Earth. And as you can see, this is about 60 seconds or so. It doesn't say this on this plot, but this is a whopping signal. And again, exactly the type of signal that we're looking for in our experiment. So we were very excited to see these two plots. I wanted to talk a little bit about target stars for the project and what kind of targets we're looking at. Of course, it's a 10-year project, and if we put together a target list 10 years ago, today it would look very different than what we put together today. So we certainly acknowledge that the targets that we're going to look at are going to be a work in progress, but I can give you kind of a first taste of what we're thinking about. So we've developed a group of about 1,710 stars that we want to look at with both Green Bank and Parks in the first year or so of the observations. And the important thing that differentiates the stars that we've selected from previous SETI searches is that we want to look at all spectral types. We're not just going to concentrate on M stars or on FGK stars as has been done in the past, but we've actually defined what we call a spectral type complete sample of stars, sort of equal bin spacings along an HR diagram. So we probe lots and lots of different kinds of stars. And certainly we could get into an argument about the lifetime of giant stars and how long intelligent life maybe takes to develop. But the truth is that there are a lot of unknowns here. We know of only one example of any kind of life anywhere in the universe, and so at least we think it behooves us to look at as many different spectral types as we can. Also included in this sample is all stars that are within 5 parsecs of the Earth, which is I think about as far as we can get volume complete in any event. And those stars will receive extra time because, of course, the nearest stars are the ones for which we would be sensitive to the weakest signals. And so that would give us the greatest chance of detecting a technology like our own. So we'll spend lots of time on those. And this just sort of illustrates that Some fraction of these will be observed with Parkes, and some fraction will be observed with the Green Bank telescope. It's an all-sky SETI program for which multiple components will be covered by different facilities. Here, I think this shows the declination cut for Green Bank and Parkes at -10. I think that's probably going to go down to -20. The Green Bank telescope is significantly more sensitive than Parkes. And again, the distribution of stars for Parkes in a couple of different forms. Here, this one's a bit interesting, the number of stars versus distance. We select the stars in each one of those bins that goes across the HR diagram by selecting the nearest stars. So we preferentially select the nearest of the different spectral types that we observe. We're also looking at galaxies. We're kind of in the early stages of putting together our galaxy survey catalog. These are just some targets that we've selected from NearGalCat, which is pretty much a canonical nearby galaxy catalog. For those of you that know something about this, there are some galaxies here that are labeled as elliptical, which are not in fact elliptical. But again, a similar program to what we're going to do with nearby stars. Some will be observed with Green Bank and some with Parkes in a variety of different modes at a variety of different wavelengths. But not only stars and galaxies do a SETI target catalog make. We'd like to look at other targets as well. Certainly known Earth-like extrasolar planets or exoplanet systems are going to be very high on our target list. It seems like every month or two, again, thanks to some people in this room, we're hearing about planets that are more and more like the Earth 2.0, 3.0, get to 5 or 6.0 here pretty soon. And although we want to keep our options open, we want to look at as many different types of systems as we can. Systems that are like our own solar system or planets that are like our Earth in terms of mass and distance from their host will certainly occupy a key part of our target list. We're also interested in kind of more speculative things. We're very interested in these serendipitous alignments, something we call eavesdropping SETI, in which a couple of folks here have recently told us might also be a good orientation to detect leakage from energy transmission systems that are used to propel spacecraft. And of course, with the huge number of multi-planet systems that Kepler is detecting, we can time our observations of many of these systems to just when these two planets are aligned relative to the Earth. There are a variety of suggestions in SETI about using natural astrophysical sources as some kind of an amplifier for a signal from a technology. And one example of that comes from Jim Cordes at Cornell, who suggested that you could use an astrophysical maser to amplify a narrowband signal that you might send through the masing column. And again, a speculative idea, something that we surely don't do on this planet. But when you have 20% of some of the world's largest radio telescopes, you can explore things like this. We were also interested to read from Roseanne DiStefano recently about her idea about searching for ET in globular clusters. I think I'm just going to paraphrase her argument a little bit. The idea is that stars are very close together here, so you might get preferential formation of star-faring civilizations in an area of the galaxy where stars are very close together. It turns out that this is kind of interesting because there are other reasons why radio astronomers like to look at areas where there's very high stellar density, notably astronomers that are looking for millisecond pulsars. So there's quite a large fraction of Green Bank telescope time that's already being devoted to looking at globular clusters, to time pulsars and search for new pulsars. And so Scott Ransom, who's a good friend of ours who leads a lot of that work, is going to work with us to actually do a SETI search alongside the pulsar work there. So a great sort of 2-for-1. They get a little bit of extra time on globular clusters, and we get a pretty significant augmentation to our program at the GBT. So we want to look for lots of different types of signals. The sort of canonical thing that we look for in radio SETI is a narrowband signal, just a simple sinusoid. There are lots of reasons why we do this. They're very robust to the interstellar medium. The narrowest astrophysical features are some hundreds of hertz wide astrophysical masers. So if you see anything that's narrower than that, as far as we know, an unmistakable indicator of technology. And this is just a plot of one of those. This is time versus frequency. This is a 1 hertz resolution spectrum from an observation on a Kepler object of interest. But you see there's some drift in this signal. This is not a signal from an extraterrestrial. This is a signal from a satellite. But you see that it's drifting in frequency a little bit, and that's because there's a relative acceleration between us at the telescope and the source. And so for a satellite that's orbiting the Earth that we know about, we can, of course, correct for this precisely, so it'll all go away. But if this transmitter were coming from a very distant planet, and we didn't know what the acceleration were, we would have to search in Doppler drift space, what we call it, to find the acceleration drift rate of the signal. This is akin to de-dispersion in pulsar astronomy. And so we're trying to develop high-performance algorithms to do this. This is a tree algorithm that we employed a couple of years ago, and we're working on speeding this up on graphics processing units. We're also interested in other types of broadband signals. A common sort of point that's raised by communications engineers when we talk about SETI is, hey, early on in the history of our own technology, we used lots and lots of CW signals, lots and lots of narrowband signals, but for a variety of reasons, we're actually doing more broadband communication now. This is an example of a binary phase shift keying waveform. You can transmit a lot of information this way. It's very robust to interference with other transmitters. So maybe ET is doing this, and if they're doing this, the power spectrum, which is what we do for our Fourier analysis, wouldn't be a very good way to detect it. And a much better way would be something like an autocorrelation analysis. So this is really a subject of active research in SETI. This is something that we're thinking very hard about, and also trying to take advantage of developments in this field that come from outside of astronomy, so from the signal interception community and the like. We're also playing around with machine learning a bit. It just sort of sounds like machine learning and extraterrestrial intelligence should go together. So we thought that was a good thing to explore. We have a graduate student at Berkeley named Isaac Shivers, who spends most of his time looking at supernova with Alex Filipenko, but we convinced him to play around with SETI a little bit. And so he's taking some of the machine learning approaches that the supernova community have used and trying to apply it to SETI. This is just one example from a paper he's working on where he's using a local outlier factor ranking approach. So he takes a waterfall plot. This is time versus frequency. You see this a lot in radio astronomy. And here are a couple of different signals that he's detected. And he kind of decimates the signal in a sort of a two-tiered way. He breaks it into a coarse resolution image and a fine resolution image at the center of the detection, and then looks for anomalies. And we're very excited about the kind of early status of this. Isaac has found some interesting signals that we didn't detect before. He's running this on a raster scan of the Kepler field that we actually completed with the Green Bank telescope some years ago. But again, we're very excited to incorporate this into our search pipeline because it gives us sensitivity to signals that we can expect, whether it's narrowband or BPSK, just something that's generically anomalous about this point in the sky versus that point in the sky. So all of this is going to be put together, at least we hope, into something that we call an open source SETI analysis toolkit. So many of you probably know that if you want to do an image extraction on an image from an optical telescope, or you want to do a spectral line experiment with a radio telescope, you can open up the observing guide to the telescope, and it'll tell you exactly how to do this and where to download the software to do your experiment. But that doesn't exist for SETI. The word SETI doesn't show up anywhere in the Green Bank Telescope Observer's Manual. And there is no canonical set of SETI search software. There's not an APES or a CASA or a Presto or a SIGPROC or anything like that for SETI, but we would like there to be. And one advantage of doing that from the ground up is that you can incorporate lots of interesting technologies that allow collaborative cloud-based analysis, things like the Google Cloud Platform or Docker and Jupyter, an interactive Python notebook. So if you're interested in any of this, please get a hold of me. We're very interested in moving forward with this quickly. Again, with the idea that this work would enable many other people to do SETI searches that perhaps hadn't been able to do it before. We're also going to distribute breakthrough listen data to SETI at Home. Maybe some of you have SETI at Home running on your computer or have run it before. This is a distributed computing application, one of the first distributed computing applications ever, in fact. And the way that this works is we take a small amount of the raw data from the telescopes where we observe, and we send it out to volunteers that download and run this program on their computer. And then the very computationally intensive analysis that's required for SETI searches are actually performed on people's home computer. And SETI at Home is actually capable of doing something very cool that our in-place analysis can't do, and that's correct for that Doppler drift that we talked about in a coherent way. So when we do an experiment at a telescope with computing hardware that we bring there, we have to detect the data, compute the power first, and then correct for the drift, akin to incoherent dedispersion with pulsars. But what SETI at Home does is it corrects for that drift in the time domain. So it applies a chirp function to the raw voltage data from the telescope, and it can remove that drift very, very accurately. And because of that, it can get to very, very fine spectral resolution, down to maybe 1/100th of a hertz or 1,000th of a hertz. And that allows it to increase its sensitivity dramatically to an inherently narrowband signal. So although SETI at Home can't look at a lot of the radio spectrum, the bit that it can look at very, very closely. And of course, we're going to distribute these data to all of the SETI at Home volunteers. There's something like a million or so semi-active volunteers at SETI at Home now, both data from the Green Bank telescope and the Parkes telescope. I showed this in Europe a couple of weeks ago, and someone told me that it looked like the U.S. was just launching ICBMs at other countries. It kind of does look like that. But this is it's real data, actually, that comes out of our web servers, and we use a little geo-IP thing to convert it into a latitude and longitude. We're also very cognizant of future opportunities for SETI. The Parkes telescope and the Green Bank telescope are certainly fantastic facilities. But as far as the rest of the world is concerned, we're moving to arrays. And a big example of that is the square kilometre array. The first two components of the SKA are going to be Meerkat in South Africa, 64 15-meter dishes, something like a southern version of the Jansky VLA. And then SK1 Low, a low-frequency aperture array telescope that's going to be built in the Australian outback. And also the Chinese are moving very quickly on FAST, which I soon won't be able to say that Arecibo is the most sensitive telescope in the planet. This is quite far along. Something like 2/3. This is a computer-generated image, which I actually didn't know when I first saw it. But something like 2/3 of the panels are now complete. So it doesn't actually look too different from this at this moment. I wanted to take a bit of time to talk just about the square kilometre array and what that will mean to SETI. And this is work that I've been doing, kind of preparatory work with a group that's involved in the Cradle of Life Science Working Group for the SKA. One of the world's largest scientific instruments, really a huge construction, probably a $3 or $4 billion project when all is said and done. That's being built by a whole partnership of countries. It's headquartered in the United Kingdom and actually being built out in Australia and South Africa. Phase 1 of the project is cost capped at 650 million euro, and something like, I think, 30% or so of this is already secured. So it's quite mature. And the precursor facilities that I showed you earlier, Meerkat in South Africa and the MWA in Australia, are themselves fully funded. So they will absolutely happen. And MWA is online now, being expanded over the next 18 to 24 months. Meerkat will probably see first science in the next 12 months or so. And this will be a fantastic telescope for SETI. This illustrates an extension of the square kilometre array that will extend it to what's called mid-frequency aperture array technology. So taking the technology that's used for low-frequency telescopes like this, where you can see the whole sky, and extending it up to a few gigahertz. And this will be great technology for SETI. There's I think a very important philosophical aspect of SETI on the SKA. Of course, as you might imagine, you get a square kilometre of collecting area, and you get a very sensitive telescope. This is minimum detectable isotropic radiated power versus frequency, and this is the level of an airport radar, and this is the level of the Arecibo planetary radar. So lower is better on this plot. But the really kind of special thing about the SKA is it'll be the first radio telescope that would be sensitive to Earth-level leakage radiation from an Earth-like planet. So even though we talk about detecting TV stations and radio stations, the truth is that none of our existing experiments could ever detect radiation, isotropic radiation, at that level. But the SKA will be able to do it for a few nearby planets, and so that's very, very exciting. For the first time, we could really detect ourselves. We're also excited about synergies with upcoming space missions. Certainly, TESS is going to tell us about a lot of very nearby transiting exoplanets that we can explore, and we like those a lot for the eavesdropping SETI and for other reasons as well. And if we want to look at a million stars, we're going to need a million-star catalog, and Gaia is going to give us a billion stars, so a million of those I think will certainly be great for our SETI catalog. In the last sort of couple of minutes, I just wanted to touch on some of the work that our colleagues are doing elsewhere that is itself really, really fantastic, not currently a part of Breakthrough Listen, but great work. The Allen Telescope Array is it lives. It is not completely defunct. Something like 12 hours a day are actually used for SETI, and they're doing a number of different SETI experiments. It's a multi-beam SETI system, so this is the primary field of view of the telescope and a number of tight array beams that are being formed up on a couple of sources here showing it over the galactic center. The most recent upgrade to the telescope that's actually ongoing is an upgrade of the feed system. So this is a log periodic dipole feed. It's a novel type of feed for an astronomical radio telescope. The original feed had a frequency range of about 200 megahertz to 10 gigahertz and an 80 Kelvin system temperature, which is pretty high by radio astronomy standards. There's a new feed that's going up on the telescope, designed again by Jack Welch, that is cut in size by a factor of 2, which gives it a frequency range of 500 megahertz to 15 gigahertz, but importantly, a much lower system temperature, and this whole thing is enclosed in a big glass bottle. Our commensal experiments at Arecibo continue. This is sort of the bread and butter of SETI at Berkeley, the SERENDIP program. It's been going on for longer than I've been alive. The search for extraterrestrial radio emissions from nearby developed intelligent populations, which we owe to Jill Tarter and NASA in their sort of likeness for acronyms. And with this experiment, we use now any receiver that's in place at Arecibo, and we send those data both to SETI At Home and a companion project called AstroPulse, and we also analyze it in place with an older generation of digital hardware. Between 2009 and 2012, we got about 6,000 hours with alpha, and analysis of these data are in process, and we're moving forward with that. Shelley Wright, who's recently took a professorship at UC San Diego, is doing some very cool work with near-infrared avalanche photodiodes. She has the first experiment that's sensitive to nanosecond scale phenomena in the near-infrared. And she has a couple of papers that have come out describing the instrument, and there's a couple more observational papers that are coming. And this is really, really fantastic work that we're very excited to work with Shelley on. I have a student with Heino Falke out in the Netherlands who's working on SETI with the low-frequency array, this low-frequency telescope that we talked about before. A graduate student at Radboud named Emilio Enriquez is doing a multi-beam SETI search. And this is a really fantastic thing that you're able to do when you have one of these multi-beam SETI systems, and that is that you can put different beams on different targets, and then you can just use the fact that the astrophysical thing, the astronomical thing, should only show up in one beam, and the interference, because it's probably coming in the side lobes of the antenna, will probably show up in all the beams. So here's an example of an 8-beam system where 7 of the beams are on nearby M dwarfs and 1's on a pulsar. So you should detect the pulsar only in this beam and not in the other beams, and sort of commensurately with signals from extraterrestrial intelligence. Here's an illustration of that. Here's the beam that's on the pulsar. You see the pulsar very brightly. The beam that's not on the pulsar, you don't see it at all, but the interference you see in both of the beams. And that's a very good discriminant against interference. There's also been all kinds of fantastic other experimental and theoretical work on megastructures and mega energy. Jason Wright has, I think, nearly published a book on WISE searches for Dyson spheres. Michael Garrett has done an extension of this using the mid-IR radio correlation. It's very, very exciting. Looking for transits in Kepler data. Also, some work that's come out of the group here that I already mentioned is really, really interesting, giving us another very good reason to look at systems where two planets are aligned relative to the Earth. Recently, Renee Heller and Ralph Pudritz published not just a theoretical treatment, but also a target list of stars that see the Earth as viewed from their vantage point transiting the Sun. So perhaps these stars would more likely have detected the presence of the Earth or life on the Earth and might be beaming us a message. There was this very fun story from a few months back, KIC 8462852, which got quite a lot of press, and I think it's fair to say that that this star, it shows a very anomalous. I'm sure most of you are familiar with this, but it shows a very anomalous light curve, very deep asymmetric transits in Kepler data. It's gotten quite a lot of attention, both from the press and from the academic community. And as far as I know, I haven't heard any sort of more convincing explanations for what's going on here than the cloud of comets. And I think that says a lot about the potential sort of interestingness or novelty of this source. And certainly we'll be looking at this quite a lot with Jason and Tabby in Breakthrough Listen. So it wouldn't be a SETI talk if I didn't put this equation up on the board, which I think has seen sort of quite a lot of fun poked at it over the years. But I'm not going to go through this whole thing, but I just wanted to point out something about this equation that I find very, very compelling that wasn't really obvious to me at first glance. And that is that by measuring n, this is the number of detectable civilizations we might detect, you actually get a handle on L, the average lifetime of a civilization. So perhaps, in fact even probably, the ultimate thing that's going to determine whether or not we're going to be able to get in contact with another advanced civilization is going to be the lifetime of the civilization, how long they last, which is I think a scary thing maybe to think about as human beings when we consider our own trajectory in the world. What might life be like 100 years from now on this planet, or 1,000 years, or 10,000 years? Could we, eventually become a star-faring civilization? Could we have habitats in space, as this kind of 50s cartoon suggested to us? In the far future, can we survive for 1 million years or 2 million years? Could any civilization become that technologically advanced? Would their technological trajectory even continue in a way at all similar to the way that our own has continued? And really, the big question: can we survive our own technological development? And that sort of brings us to the end of the talk, which is by studying another civilization's past, we get a glimpse of our own future. I didn't come up with this; Philip Morrison did. He called this the archaeology of the future. But I think it's a really sort of compelling idea to leave a talk with SETI on. So thank you.
We have time for some questions.
Yep. Two quick questions. One is, do you have a protocol if you detect something that seems credible, and what is that? And the second is, a lot of the wavelength regions that you are surveying understandably correspond to regions of high transmission in our own atmosphere. But a lot of the candidate planets you're looking at may be 1.5, 2 times the mass of the Earth, most likely have much denser atmospheres. Have you run atmospheric models for such planets to see where their transmission zones might exist, and perhaps find an overlap, between as many varieties of planets and their atmospheric transmissions?
Yeah, so maybe I'll start with your second question. That's a really good idea. I like that. So maybe we will do that. I mean, the kind of telescopes that we use and the kind of searches that we do are kind of as much driven by kind of our own technological development and kind of pragmatism than they are anything else. I mean, we sort of search where we can, like the drunk looking for his keys under the street lamp. But I think doing the work that you described would be very interesting, and sort of looking at regions of overlap and concentrating our searches there. That's an interesting idea. Your first question about whether or not there's a protocol. Yeah, there's like a half a dozen protocols. There's a group that fancies themselves as the SETI Post-Detection Committee. I'm not on their committee. I don't have their number. So I don't, they think quite a lot about this, and they've thought about sort of how many days you should wait before you tell the president, and then, I don't know, the UN and all this kind of stuff. I mean, as a scientist, the thing that I'm most concerned about is being sure about what we're looking at, following up on it quickly, and doing a careful study. So the most important thing to me, if we detected some putative signal from another civilization, would be to keep looking at it as much as we possibly could. And we have mechanisms for that. We have ATELs, and we have the phone number for observatory directors. So that's what I would do.
Any more questions?
So you mentioned, I think you mentioned $100 million or something. What is your funding? I mean, annually, and how guaranteed is it? Is this 100 million guaranteed? This kind of thing.
Yeah, well, that's a delicate question.
Okay.
I mean, in some sense it is, in some sense it isn't. I mean, the program is 10 years and $100 million. That's a pledged number. A significant amount of that has already been committed, and some of it has been sort of transferred to the appropriate accounts, and we have funding to hire people and build equipment. I hope that it ends up being at least that much. In fact, I hope it ends up being more. I hope that this pledge from the Breakthrough Prize Foundation is looked at by governments and sort of more traditional funding bodies favorably, and that they get in the game as well. So we'll just have to see, but we're up and running.
You mentioned at the beginning a galactic survey, but you didn't talk much about that.
Yeah. You mean in terms of the sort of LB extent and integration times and bands and stuff? Yeah. Well, the lion's share of that is going to be initially covered with the multibeam receiver at Parkes. It's about 1.2 to 1.5 gigahertz. We have about 1,530 hours a year on Parkes, and roughly 30% of the time probably will go to that component of the search. We haven't made a decision yet whether it's going to be step and stare or raster scan or what the dwell times are going to be. But it will be a significant amount of time, 1.2 to 1.5 gigahertz.
Is that?
The question was asked about the funding, and I think one of the exciting things in the programs you've described is the opportunity for synergy between the types of astrophysical questions people in many different parts of our astronomy community ask, and the data that you'll be collecting which can answer them. So you mentioned the globular clusters and millisecond pulsars. In fact, if our calculations are correct, and so many uncertainties that it may very well not be, those globular clusters that are best for SETI searches are the ones that have the most millisecond pulsars. Mm-hmm. And in terms of signal recognition, all of the many different types of signals that we are trying to find in searches for transients, even though the details will be very different, some of the principles will be the same. So I think it'll be interesting for the community to think about how they can plug in, how we can plug in to be able to make this a community effort, one whose benefits spread throughout the community.
Yeah, absolutely. I agree 100%. And I think the GC example is a great one. We just got back from Sydney a couple of weeks ago. We held a community workshop at CSIRO, the CSIRO, to discuss the Parkes part of the program with the Australian community. We have plans to have a community workshop at Greenbank or maybe in Charlottesville in the next couple of months. And anybody that's interested, it would be great if they came out. We heard quite a lot of good ideas, both about SETI and about ancillary science when we were at CSIRO. There was a strong interest, of course, from the FRB community at Parkes in piggybacking, as you might expect. Also, folks that are doing OH maser searches, and also 21 centimeter maps, because of course we have essentially infinite 1 over observation time, spectral resolution, velocity resolution, if you're going to be an H1 astronomer. So there are lots of opportunities, and we really look forward to hearing about those, especially those that push the SETI part of the program forward. We would love to develop very robust interference rejection pipelines, for example, that are both useful to us and useful to transient observers, for example.
I'm still a little bit confused about what is the uniqueness in the signal that you may hope to detect that would rule out all possible astrophysical phenomenon or terrestrial phenomenon and attribute that to SETI. And what's the unique? It's the equivalent of what is the biosignature of life?
Yeah. So I think I'm not an expert at sort of disequilibrium chemistry, spectroscopy, and sort of how convincing some particular kind of spectral signature would be of dumb life. But I think based on what we know, a 1 hertz sinusoid is more obviously an indicator of life than perhaps some disequilibrium chemistry situation in the atmosphere of some extrasolar planet. But you're right. I think if we detected something that was, I don't know, say 50 hertz wide, and I don't know, had some kind of variability that looked roughly stochastic, we would have to think really hard before we were able to kind of make the claim that that is in fact technology. But that would be an incredible discovery in its own right. So that would be fine. I mean, I don't care sort of what the title of the Nature paper is. Right?
One more question.
Yeah, I just want to make a comment about this, about the external galaxies, which is, you say megaparsecs versus kiloparsecs. There's the 6 orders of magnitude in flux, so they've got to be really powerful. But if you think about it, if you want to illuminate a galaxy, it doesn't take any more power to do it from outside than from inside. If you want to have some flux going through, just think about that. You just make a diffraction limited to just illuminate the galaxy. So I think that it's really worth taking seriously that. Of course, there's always that pesky thing about the speed of light, and conversations kind of drag on for a long time.
Yeah, that's true, Paul. I think it's a different part of parameter space, and this in many ways is a game of exploring parameter space, and so we're very excited about it. There's been only sporadic SETI done on mostly very nearby galaxies, the Magellanic Clouds thus far, so we're excited.
Quickly.
Yes. I guess the catalog question is the thing that kind of comes to my mind the most here, which is there's lots of things to potentially look at. And we only know of one place where life's developed on a planet. So in the catalogs, have you guys taken into account the question of time, like how long the particular stars are in that catalog that have been around? And similar to our kind of story, to have that be the center of the distribution?
Yeah, sure. I mean, most stars are longer lived than our own sun. So there's that. And we certainly think about the lifetime of stars, and this is a common thing that's brought up when people suggest that you shouldn't look at large stars because they have such a short lifetime. But that said, I'll reiterate this point that we know of only one example of life anywhere in the entire universe, and so to sort of extrapolate too far from that, I think, might not be such a good idea. So we try to keep our options open as much as we can.
Okay, I think that's all the time we have. Andrew will be here through mid-afternoon tomorrow. So if you want to meet up with him, please look at the wiki page that was sent in your email. And let's thank Andrew again.